Thank you, Ned. So let me start by thanking Ned and Dave Chalmers and Raphael Milliere for organizing and for having me along. It's been a real great treat to be in this as an interdisciplinary philosopher, to have computer scientists and people from different bits of cognitive science all wanting to talk to philosophers. It's been really fun already. I also wanted to thank Raphael for organizing the deep learning reading group week in, week out for the last 2 years. It's been a real highlight, especially at the beginning of COVID when we couldn't travel, to get together with people across the US and Europe talking about deep learning. And with these developments coming out like weekly and monthly, a lot of what I've managed to learn about the new developments has come from talking to people in that group. Raphael often gets the speakers in, the authors of papers in, and then there's an awful lot of other experts, some of whom you've already heard from. So that's been a real highlight for me. Thanks for that, Raphael. So we've seen today, over the course of this weekend already, that one of the philosophical bits of interest about deep learning is what it can potentially tell us about how to model the human mind. That's what I'm going to be focusing on today. And I've long been an advocate of the claim that artificial neural networks are an interesting and interestingly different way of modeling some aspects of cognition. In fact, I worked on it right back in my PhD. So it was a bit disappointing when for years and years and years, deep learning, artificial neural networks weren't being used in any practical applications. It looked like maybe they, although philosophically interesting, they weren't going to actually work for anything. So then it was a massive relief, having worked on it, when in 2012, they started actually doing something useful. And that wasn't just a kind of I told you so moment. I think what we're going through now is actually some kind of gestalt shift, some kind of quite big transition in what we see as the range of possibilities for what these machines can do and how we can model cognition. And I think it's a bit of a gestalt shift, a bit like the one that René Descartes faced nearly 500 years ago. So this is an automaton, a mechanical device that was set up to move in roughly biological ways. This one's created in the 1560s and now held in the Smithsonian. It still works a bit. And what you can see, although it's very crude, is that it might just give you a sense of biological motion. It might fire your capacity, as we now say, for detecting biological motion. And for Descartes, that was a revelation. Things like this, machines that could produce something that looked like agentive motion, were producing something that up till then had been thought to be special, something only animals can do, something that maybe came out of a special life force. And this was part of the inspiration for him on seeing this new possibility of generating his whole mechanical philosophy. But of course, famously, he thought that the mind was an exception to that. Most famously, consciousness and the difficulty of conceiving how physical or mechanical processes could produce consciousness, creating a hard problem that we're still grappling with. But for today, even more relevant, he thought the same thing applied to language. He said, of course, we can think of a machine as saying words, but producing meaningful sentences, not only is that impossible, that's inconceivable. Here he is writing that. We can certainly conceive of a machine so constructed that it utters words, but it's not conceivable that such a machine should produce different arrangements of words so as to give an appropriately meaningful answer to whatever is said in its presence, as the dullest of men can do. Well, of course, now we can see that that's possible. And we were making progress on that already in the 20th century with classical computers set up to make meaningful, intelligent, you might say, transitions between representations using the principle of implementing broadly logical transitions. So making the kind of inference there about Socrates being mortal is the kind of thing that until the 20th century, only people could do. Only intelligent people would move between representations in that kind of way. And we found that in the 20th century, it was a big discovery that we could set up machines to do that and many different other kinds of logical inferences by setting them up to have a disposition to move between representations based on their form or their patterns. So if you set up a machine so it's disposed to move between representations that fit this form, then you'll end up with something, this form, you'll end up with something that can make transitions between representations so that it will move from representations. If you input true representations, it's bound to get true representations at output. That principle turned out to be, it's at the heart of almost all the computers we're still using, turned out to be incredibly useful practically, also useful for understanding quite a lot of what's going on in the mind, but yet didn't take us quite to the thing that Descartes found inconceivable, which was giving an appropriately meaningful answer to whatever is said. It's only really in the last 3 years that we've got machines that can do that, as we've seen a lot of already this weekend. And I think adjusting to that is a Gestalt shift. It expands the space of realistic possibilities for modeling aspects of the mind. What it's shown us is that training specific dispositions, end to end, you might say, to respond to inputs with specific kinds of outputs is much, much more powerful than we ever previously thought. And I don't want to downplay the importance of that discovery. In a way, what I'm saying is a reaction to that discovery. But what I want to do today is to say that this isn't just a matter of a choice between the classical architecture and the connectionist architecture. When the connectionists have won, actually there are complementary costs and benefits to both approaches. And we shouldn't overlook the importance of what you might call broadly logical reasoning if we want to characterize the aspects of human cognition as a whole, if we want to go beyond doing what the dullest of people can do. And what I want to do today is to characterize that difference in a particular way so as to show why there are characteristic benefits of what you might call broadly logical reasoning that are complementary to the costs and benefits of processing representations in the characteristic way that deep neural networks do. The package of the classical package is kind of familiar, doing what I'll characterize more specifically, but that you've seen an example of already, broadly logical reasoning. One way of doing that is through variable binding, being able to do that on representation that are stored in the form of explicit representations of memories or stored knowledge, and you doing it on representations that show a general purpose form of compositionality. And that's contrasted with the deep neural network package. I want to drill down to a particular way of drawing the contrast that I think can help us see why there are complementary costs and benefits. So the plan is to say a little bit about how I'm thinking of representation in deep neural networks quite quickly, just to lay the foundations of where I am in terms of what representations are. Then to draw this distinction between these two broad ways of being set up to make transitions between representations, between what I'm calling the content-specific way and the non-content-specific way. Then I want to argue, as the central argument really, that when we're modeling human cognition, we need to see it as being able to access both styles of representation processing, both types of computation, and to move flexibly back and forth between them, given their proper domain of operation, given their complementary costs and benefits. And then at the end, I'll say a little bit about whether something like this is going on in our AI systems too. So to think quickly about what representation is in deep neural networks, I'm going to use the very most simple system to illustrate this. And this is an old neural network with 3 layers, trained to categorize some stimuli, which are objects. You code properties of the objects at input and train it at output to sort them into the A's and the B's, say. And the way that it hits on of doing that is to sort the objects into different individual objects at its intermediate layer. So it finds a pattern in the data, which is also a pattern in the world. The intermediate layer comes to carry information about that pattern, and it uses that sort in order to perform the output task, to classify the A's from the B's. So there we've got the ingredients that I would say go into there being representation here at the hidden layer. We've got carrying information by vehicles of content in the service of performing a function. In this case, the function comes from what the system's been trained to do. And it's important that we're being realist here about representation. We get extra explanatory benefits for there being real vehicles of the representations in the ways that they're being processed. So the vehicles might be clusters in the activation space, as you see on the left there, or they might be dynamic trajectories in an activation space, as you see on the right there in some monkey recording data. They could be polytopes or some other kinds of manifolds, but it's important that the representation content's being carried by things that are real features of the way that activity is being processed through the network. That's to say, if you were characterizing the dynamics of the processing being neutral about contents or representation or which way information is being carried, these are things that would still exist. They're not just existing relative to representation explanation. That's what makes it a realist form of a representation explanation. And although most of the work in deep learning is about getting the outputs, getting technological solutions, there is quite a line of work, as we've already seen yesterday, looking at whether there are representations in inner layers, what are sometimes called inner representations. This is work on autoregressive language models, including GPT-2. And what they were doing, Meng and colleagues in this study, was trying to find if there are parts of the inner processing that are carrying representational content that's important for performing the task. Here, the task is just predicting the next word. So for example, after training, it can complete the sentence, the Space Needle is in downtown something, complete it correctly with Seattle. And they want to know, are there particular bits of the processing that are important for being able to perform that task? So they perturb the input, degrade the input, and then do a causal mediation analysis to find if there are particular bits of activation that are most important for getting the right output, where if you fix them, you get closer to getting the right output. And what they find is that there are some patterns of activation in early layers that are important, and then also there's a late component. And so the hypothesis is that having seen the subject of the sentence, the Space Needle, the system has learned to go into a bit of high dimensional activation space that is representing Seattle. And then that embedding sits there ready to be used when it becomes relevant later in the sentence. And then the late activation is an attention head calling on that information so as to look up the correct word and output Seattle. So if that hypothesis is right, then the system has learned something they call an association. We can just think of it as a learnt specific connection between one bit of one activation space that's in yellow there on the left, and another bit of another activation space in light green. It's connected the Space Needle bit of the embedding space to the Seattle bit of the embedding space. That's how it's learned this piece of information that's important for getting the right answer for this particular sentence. And that's a useful way of storing information, but it's got limitations because the information that the Space Needle is in Seattle is just stored in this disposition. So it's not available to be used generally for computation. It's set up in this representational disposition. Contrast what we can do with the sentence, say that the Space Needle is in Seattle. We can reuse that sentence. We can do all kinds of processing on it. We can reuse it in multiple contexts. The information that Meg and colleagues discovered in their network is represented implicitly in a specific sense. It's implicit in that the content is stored in a disposition to move between current representations, between patterns of activation, which means that the only influence that information can have on subsequent processing is via the representations between which that disposition exists. So that's a limitation on what you can do with implicitly represented information. But of course, these networks can also represent information explicitly. And here's some other work looking at how another autoregressive language model is representing information. This is one that's trained on lots of language and then fine-tuned on a particular range of tasks that are about adding and subtracting water from fluids from beakers. So in the middle there, you can see one of the sentences it might give. The third beaker has 4 in it, sees a lot more sentences, 4 blue, and then eventually you drain 2 from the third beaker. So what you should expect that is, it should now think that there are 2 items of fluid, units of fluid in the third beaker. And for all those kinds of possible intermediate states, they go into the network and see if there are patterns of activity that are particularly carrying that information and important to performing the task. Now, this is really difficult to do methodologically, and I've got some methodological concerns with this, but it's getting at the thing that I'm talking about, which is an explicit representation of a piece of information. And then having represented explicitly this temporary fact that the third beaker has 2 blue units, that can be used multiple places downstream. So it's explicit rather than implicit in the Space Needle case. But again, the way that it's used depends on its very specific content. So it's set up to interact with other representations of things about beakers and fluids and adding and subtracting in a way that depends on that specific subject matter. It's a disposition to move from one bit of activation space to another bit of activation space that works for this particular subject matter on which it's been trained. And I think that's often true, or maybe very generally true, of deep neural networks. So here's some earlier work on a network, convolutional neural network trained to do image classification. And again, getting at what's actually going on internally is very difficult methodologically, but there's some data here that suggests at least a picture where in the early layers of processing, it's doing something similar to what we think is going on in the early layers of processing in the human ventral stream. That's to say, it goes from representing things like contrast and edges to representing textures and then parts of objects on the way to being able to classify objects. So these are a good set of dispositions to have to move between representations, to move from a certain distribution of contrast to a representation that edges are in such and such places. They work well in the statistics of the human visual environment, but they're not generally applicable. They're applicable to that subject matter. They're transitions that are faithful to content. They're kind of correctness preserving transitions, but that are trained on a specific subject matter and work for a specific subject matter. Contrast that with the Socrates inference we started with, that was at the heart of classical computation, where that pattern works more or less whatever subject matter, right? You can substitute other things for Socrates and mortal and human, and you'll still get a necessarily truth-preserving transition. And that's the contrast that I want to draw. So let me give a couple of other examples. Other examples are logical and deductively valid, like and elimination. That'll work for any propositional size representations, or using if-then, again, works very generally for representations of particulars and properties. But this doesn't just depend on deductive validity. We get this very general applicability to other kinds of transitions where the conclusion is not bound to be true given the premises, it's just very likely to be true. So you might set up a system, we might be set up to move from estimating that something has very high probability to just representing it outright. And that's not a bad disposition to have. You won't go very wrong very often with that kind of disposition. And it's very generally applicable, a bit less generally applicable than the deductively valid ones, but still very generally applicable. And similarly for generalizing from a sample to a population or a new instance. So we've got a bunch of examples there that contrast with what I think is typically going on in an artificial neural network, in that they're much more generally applicable, and they're being faithful to content, roughly they're being a useful way to be set up to transform representations, doesn't depend on the specific contents that are being represented on, as you might call it, the open class concepts. One way to do that is through having schema and using variable binding, but that's not the only way. A system could be properly described as meeting one of these, maybe meeting the disposition to use if-then, if the generalization I've written down there just describes what it's doing. So this might be true of the outputs of GPT-4. It might be that it's properly described as meeting the conditions on using if-then between its representations, but without using variables at output. So this is the contrast I want to draw. These are the non-content specific transitions. Contrast with the content specific transitions that typically get trained into a deep neural network, like I gave you with the Space Needle example, or with the way that the representation of the amount of fluid in the third beaker is being processed. So I'll just put that up, put a precise way of saying this up on the screen in case anyone wants to come back to it later. What this transition is turning on is whether the faithfulness to content of transitions between representations turns on anything other than the logical terms. So for the ones that are like logical reasoning, they're faithful to content because of the content of terms like and or if then, but not the other representations being used. Whereas the content specific ones, they can be good ways to be set up to process representations, but that goodness will turn on the specific contents that are being processed. And then when I talk about broadly logical reasoning, or sometimes just in short reasoning, I'm talking about things that are set up to be able to do these non-content specific transitions and are doing them. Okay, so that's the distinction. And I think that's probably not unfamiliar. We saw in Ishita's talk yesterday when she was talking about reasoning, her spelling out something very similar to that. What I wanted to say is that this way of thinking about a special capacity for transition between representations shows us some of the reasons why it's got particular benefits to be able to process representations in this way. So one reason is because it gives a system, a thinker, a person, something to do with representations that lie far outside their trained experience. So going to the history of science, we can think of Albert Einstein, who was doing lots of logical reasoning and mathematical reasoning about space and time, and then at some point formulated the thought of what would it be like for a person to be flying on a javelin as it got close to the speed of light. So that might be entirely beyond the experience of any of his trained
information processing dispositions. Nevertheless, he could do something with that representation. He can do logic on it. You can, although it's new from the point of view of any of your built-in ways of reacting to representations, you can go to new places by doing a bunch of logical operations on that and other, on other representations in a way that's not a matter of generalizing from experience. So it's often remarked that compositionality as a feature of representational systems is useful because it allows people to think new thoughts, or allows a system to generate representations of new possibilities. But what's less remarked on is that you've got to be able to do something having represented a new possibility. You've got to be able to process that representation in some useful way. And what the capacity for non-content specific computation gives a system is a way of processing those completely new possibilities, representations of completely new possibilities. So I think there's a useful package here between the capacity for very domain general compositionality, for putting together existing representations in new ways that don't depend on their specific contents in the way that's characteristic of language and probably conceptual thought. That goes together naturally with the capacity for non-content specific computation so that the system can do some bunch of useful things with those new representations. So that's one benefit. And another one is related, which is the capacity to do something with stored explicit memories. So deep neural networks have two different ways of dealing with the past. They engage in learning, they change weights, and that's a matter of changing dispositions to deal with future inputs. So you learned something from the past by changing this whole state of the processing system so that it's disposed to deal with inputs differently in the future. And of course, there's another way that they deal with the past, which has turned out to be very powerful, which is to change its activation state, to make a transient change to the state that you're currently in. And with transformers, that can be very, very rich and branching. So the context to which the system's responding by going into different states can now be thousands of words long. And combining that with clever prompt engineering has made that a much more practical way of dealing with the world than anyone, I think, previously thought. But nevertheless, it's a matter of the system having a bunch of different, very, very detailed input-output dispositions for different inputs. So think of a kind of naturalistic scenario. I'm out foraging, I see a tree and it's about to come into fruit. Right? That piece of information might be good to affect what I choose to do the next day, whether when I get to a certain junction, I turn left or turn right, might depend on whether this tree, ought to depend on whether this tree was fruiting or not. Now we can treat those two different possibilities as long chains of input. There's one set of inputs where I see a non-fruiting tree, a bunch of things happen to me, and then I make a choice the next day, output one, and where I ought to do something different, fruiting tree, another same chain of different inputs, I ought to produce output two. I can be set up to react differently to those two different inputs. But the past could be more than a day ago. It could be a week ago, a month ago. It could be something that I saw last year. And a point that Randy Gallistel has been pressing for a very long time is that there's an in-practice limitation on setting up a style of computation that deals with the past by building in changes to the processor, by committing processing resources to dealing with all the different paths that you might encounter. He calls it the infinitude of the possible. It's just that there are so many different chains of possibilities you might have to deal with that you end up committing an awful lot of processing capacity to dealing with the things that you might see. So Gallistel was arguing that that's a practical limitation. We need to build our practical computers in a way that doesn't commit to this problem. He might be wrong about that. What we might be seeing just in this moment is that it's not a practical limitation, that for the kind of engineering solutions we want, we can do it with this very long input disposition solution. But I think when we come to humans with different resource limitations, there's pretty strong evidence that we use a different solution, which is that we store explicit memories. So we can encounter a situation, store a representation of it without yet changing our dispositions to deal with inputs, and then at decision time, make use of it if it's relevant to calculate what to do. And that's something that we also see in some of the deep neural network models. You saw an example of DQN yesterday. So there it's talked about as using episodic memories, but that's a matter of storing situations without changing weights yet, and then using those situations to decide what to do at decision time. And it gives you a kind of flexible one-shot learning, because if you come across the same situation again, you can just do the same thing again to get a reward, for example. So then we see that there are these two broad solutions for dealing with the past. There's the deep neural network solution, which changes its input-output dispositions, which is very learning heavy and requires large amounts of data. This is all familiar, although I was quite struck yesterday that the amount of energy that it takes to train a transformer is going to the moon twice and back. So when I say it takes a lot of training, we're really talking about a lot of training. And then it's relatively computation light at decision time, because what to do in a way is already pre-specified, even if it might be dealing with a very long train of inputs. On the other hand, we've got computing with explicit memories, which is learning light, allows one-shot learning, but then is computation heavy at decision time, when you need to work out what to do, or when you're carrying out some inference to work out, to draw new conclusions or work out what's the case. And it also raises the problem of what to compute with. If you stored all this rich bunch of memories, which memory should I draw on to work out what to do at a moment? And there we see the familiar, if rather faded into the background, frame problem, which I'll come back to. Okay, so those are a couple of benefits with having the capacity for non-content specific computation. What I want to argue now is that humans flexibly rely on both kinds of processing. I'll just give you an everyday example. So suppose I'm out shopping, thinking of buying furniture, and one of the things I'm thinking about is buying this chair or which chair to buy. So one thing I might do is do some logic. I might see two chairs with just the same specification, and one is cheaper than the other. I'll rule out. But I can also rely on information that's been trained into my special purpose systems, that it's got these content specific dispositions. Or just to put it more in a more common sense way, if I'm thinking about, for example, can I take the chair home today? Will it fit in the car? I can rotate it in my mind's eye and see whether it looks like it will fit in the car if I buy it. And there, what I'm doing is I'm relying on information that's been trained into my sensory motor capacities, probably in the human case with quite a lot of evolutionary endowment about how those things learn. But I've got a set of sensory motor dispositions that I use when I'm interacting in the world, and I can run those offline in a simulation in order to rely on the information that's in them. So then I'm going back and forth, or using both my capacity for logical reasoning on this question, and also using the information that's trained into my domain-specific systems. And I think planning typically does involve this kind of hybrid. So we saw Jan LeCun on Friday night talking about planning and how you need to have a world model over which you can compute possibilities. And I think it's important to remember that world model might not just be an explicitly represented set of situations over which you do reasoning. We can also use these trained content-specific dispositions that neural networks model so well. We can use those as a kind of world model by running them offline in simulations. So I think humans go in for both. And I think there's reasonable evidence that we're not just doing the content-specific thing, that we're doing logical reasoning. Now, for my purposes, it doesn't really matter whether we're doing it just with the outputs or whether we're doing it internally. I think there's pretty good evidence that we can do it with the outputs. And it might be that we do that in virtue of language and then recycle that internally in order to do logic. But actually, there's quite a line of evidence that in non-linguistic tasks and in ways that don't draw on our linguistic capacities, we do use something like an internal logic engine to work out the answers to problems or to work out what to do in certain situations. So for example, there's a bunch of work coming out of Stanislav Dehaan's lab showing results that are very suggestive of this. And there's actually a nice summary of a bunch of results in this domain in a recent BBS Target article by Jake Quilty-Dunn and colleagues. So I think there is reasonable evidence that humans are running a logic engine, but even if we're just using it as output, doing something logic-like at output in the right context and reusing it, I think we do go back and forth between these two styles, and in part for the reasons that I've given, because it gives us a way of thinking about entirely new bits of what you might call conceptual space, because we can do logical processing on entirely new possibilities that we generate with our capacity for general purpose compositionality. And also because it gives us something sensible to do with all the stored memories that we've stored when we explicitly represent situations we've encountered. Okay, so that's to kind of emphasize limitations on what deep neural networks are doing while crediting the amazing results that they've produced. Why is it that we weren't able to solve all of these problems with the classical computational style then, if it's so good, you might ask? Well, I think partly because of the limitations that I've already mentioned to using non-content specific computation. So on the one hand, I just pointed out in passing that it's computation heavy. It uses a lot of computational resources to work out what's the case or what to do. So if you're operating in a domain where you have got access to lots and lots of experience, then it's probably a more efficient solution to train up a dedicated way of reacting to the world and to rely on that. And then I just mentioned in passing the problem of what representations to compute with. So we've got this great capacity for doing broadly logical inference because we've got a way of transforming representations in a way that's neutral about their contents. But what are we going to do that on? We've got all the things that we represent, all the things that we know and remember. Only some of those are relevant. The frame problem is the question of how do I work out which of those representations are relevant in order to start doing some logic with them in order to take a decision. And if in order to work out which are relevant, I need to check them all, then it looks like I've got something that's already computationally intractable. And actually the hybrid systems in deep neural networks that make use of explicit memories at the moment, at least the ones that I know about, do just check them all. They have like a mechanism for checking them all for relevance and only recalling the relevant ones. But I think here, this is another place where the hybrid works, where the complementary costs and benefits of the two styles of computation could come into play. Because deep neural networks give us a set of options for recalling representations by relevance that are probably flexible enough to at least give us a way of coping to some extent with the problem of recalling relevant representations. So we've seen this evidence yesterday. Let me just remind you of what this study by Gran and colleagues was showing. So they're studying the way that a bunch of concepts are arranged in a high dimensional semantic space, both in a neural network and then in humans. And you can see that this space would give you a way of recalling or retrieving representations based on some kind of similarity. Maybe the things that are most relevant to the current situation are the ones that are similar. But the interesting thing that they show is that we can do recall in this space along different semantic dimensions. So we could consider relevance or similarity along the size dimension. And that will put some things close together and some things far apart. But we could separately pick a different dimension, like whether things are dangerous or safe, and consider similarity along that dimension. And then you get a quite different ordering of the same items. So just highlighting dolphin and tiger there, they're far apart in dangerousness, but they count as very similar in size. So if we're relying on semantic spaces or representational similarity spaces trained into deep neural networks, it doesn't just give us a way of recalling things based on relevance. It gives a way of doing quite context sensitive, different kinds of recall by relevance, by projecting relevance along different dimensions in those spaces. And Gran and colleagues showed that the different projections you get out of the trained language model are very similar to the ones that humans would give you if you're asking them to give you judgments of similarity along different dimensions. So it's plausible that we can recall representations, or for example, memories, in a variety of different ways. We can think of different kinds of relevance in order to come up with things that might be relevant to reason with. Okay, so I hope I've given you some sense that the content-specific, non-content-specific distinction shows us why there's like two different packages of styles of processing that have got complementary costs and benefits. And at least when we come to modeling human cognition, we need to think of something that has access to both, has some sensitivity to their proper domain of operation, and can move flexibly back and forth between them. So finally, I want to say something about the what's going on in AI models, especially large language models. So until this week, more or less, until GPT-4, I might have just blithely been able to say that large language models aren't very good at reasoning tasks, especially out of distribution. We saw from IDA yesterday that they have this very nice work showing that they've got human-like content biases, but they're probably not doing reasoning in a human-like way. We get reasoning out them partly by doing training on lots and lots of lines of computer code, and partly by very careful prompting them to output context-specific outputs in a way that's kind of encouraged to be in the reasoning kind of style. So although they're approximating reasoning in their outputs, it seems unlikely that they're generating it by non-content specific transitions internally. Now, of course, everything here is very tentative because it's very hard to know what's going on inside, and there's only a small amount of work looking at it. But a couple of suggestive lines of evidence when we come to what's going on internally. One is the patterns of errors you get, at least before GPT-4, especially when you give the systems out of distribution examples. And second, what happens when you specifically train a model on lots and lots of logic? It doesn't seem that they're very good to getting onto the logical operations that are responsible for logical sentences, if that's all you give it. And this is some work coming out of Eli Pavlik's lab with Trailer and colleagues. And they've actually got more recent work where you're not training them on logic, you're training them on physical situations where understanding the logic would be very helpful. And there again, it doesn't look like the model gets onto the underlying logic. So that's before last week. Now, I really don't know what to say with GPT-4, partly because I don't know enough about it, partly because we all don't know very much about it, but it does look like it does much better at reasoning tasks. And I think the safest thing is to say, well, we need to wait and see, but at least there's some indication that it's probably also not using a logic engine internally, both because of its similarities to the earlier models, and also because it's still not very good at planning, which is something that we might think it would be better at if it had internal access to non-content specific computation. Now, that may be not a very important limitation when we're talking about a technological solution. So if I'm right, and that there are computational benefits to having access to non-content specific computation, that needn't be in the internal processing. And I'd bet that if it's useful, it's not going to be useful building it into internal processing in large language models. I mean, the kind of moral from recent years is probably that building in structure is something that the system will either learn to avoid or it'll make it perform worse. But there's another set of ways of using it, which is using the capacity for reasoning at output. And I'll just want to mention finally 2 ways of doing that. So one is to use the large language model to produce outputs that, with the right prompting, are approximating reasoning. Let me start again. It's to use the large language model to produce outputs that are content specific, that are making use of the rich knowledge it's got of its domain, and then interacting with a reasoning engine, with Python or some dedicated logic engine, so as to be able to do constrained logic on those outputs. And that's something that we see a bit of. But there's another thing which I think is kind of fascinating, which approximates the same thing, which is to use the same model in 2 different modes using different kinds of prompting. And this is work by Cresswell and colleagues of DeepMind. What they show is that you can set up the model so that it's approximating logical inference in inference mode with the right kind of prompting, but you can also use what they call selection mode, where it's doing much more like the content-specific moving between sentences based on what people tend to say and what the statistics in the environment are, picking up on the kind of content biases that Ida was showing us yesterday. And what they show is that you can do clever things by switching back and forth between the 2 kinds of prompting. So you get it to tell you what it knows richly about the world, and then you prompt it to do logical reasoning, and then it can reason to some new things using logical reasoning, and then you put that back in as an input to the same model, but now back in selection mode and content-specific mode. So these are just hints of possible engineering solutions, and who knows where these things are going to go. But I think there are at least 3 empirical possibilities. It could turn out that GPT-4 or one of its successors manages everything, like end to end. And the thing that I'm saying is an advantage in human systems isn't needed in systems that are not limited in the same ways. It could turn out that hybrids are a useful thing as a practical engineering solution, perhaps this Cresswell and colleagues approach, but it's a relatively shallow engineering problem to add this in and to get the complementary costs and benefits I'm talking about. But it could also be that there's some deep reason why it's difficult to set up a system that moves flexibly back and forth between the 2 styles of computation and integrates them in the right way. So just empirically, I think we don't know, and it'll be very interesting to see what possibilities the modeling comes up with in future years. Okay, so let me just wrap up by coming back to my central point. So I've been arguing at the heart of the difference between these two different types of computational models, the classical and the artificial neural network, is this deep difference between two different ways that they're set up to transition between representations. Both ways that fit the broader representationalist insight that it's useful to set up a system so that it will move from some correct inputs to correct outputs, or manipulate representations in ways that are faithful to their content. But there's two quite different ways of doing that. The non-content specific way, which we hit on first as an engineering solution, and the content specific way, which has turned out to be much more powerful than people thought in deep neural networks. And I think this way of drawing the distinction, which is related to lots of other ways that we've drawn it, but it allows us to throw light on why there's a package of complementary costs and benefits to the two approaches, and why, at least in the human case, we need to model it with a hybrid system. So although the deep neural network approach of training in end-to-end a bunch of content-specific dispositions have turned out to be much more powerful than I think people expected, it still has some limitations for which non-content-specific computation offers a complementary package. And I particularly pointed to two: the ability to do something sensible with stored explicit memories, which might lie outside the range of experiences on which the system's got a trained content-specific disposition. And then relatedly, the capacity to do something on entirely novel possibilities that have been generated through the capacity for general purpose compositionality. So the system can think something entirely new, and it can also do something in terms of processing with those thoughts because it can do logic on them, even though it's not, none of the things that it's been trained to react to would be able to do any kind of sensible inference on them. Nevertheless, this style of computation has familiar limitations. The computational cost of taking decisions, and the frame problem, the problem of what to retrieve. And I've argued that having access to special purpose systems that have been trained on a domain and have content-specific dispositions is a useful way of navigating both of those kind of problems. So that's my irenic solution. The wars that were around between these two different styles of computation don't need to persist. I'm hoping that peace will break out on all sides. I don't really expect it though, and I'll look forward to your questions.
Wow, we have two of these. Okay.
Thanks a lot. That was fantastic. I just want to press you a little bit on this idea. So I think you agree, right, that current large language models can do some forms of non-content specific computation, but that's the okay. So that's what I wanted to ask you about. So can you explain more specifically what you mean by that? Because you can do, for example, zero-shot reasoning with, say, GPT-4, multi-hop reasoning that involves several steps without telling it things step by step and having some kind of prompt engineering and chain of thought reasoning. And you have many instances of this being non-content specific. You can switch the particular values of the reasoning pattern, and you will get the same performance. So how do you account for that? And in what sense is it really reasoning with the output?
Okay, so Holly, yeah, okay, good. So how to account for that is that it's not surprising that if the system's been trained on a bunch of problems that include problems that have got this pattern, that it's able to generalize the pattern. So I was arguing that non-content specific transitions don't depend on content, but they don't depend on content at all. They do depend on the content of, say, the logical connectives. And that's something that a large language model can learn and then can generalize. Although we saw that there are limitations on that, if you try and get them to exemplify the pattern with like new non-words, then they're less good at that than they are with familiar content words. So, but I'm not resisting the idea that given that those are the patterns in the training data, then the outputs can start exemplifying those patterns. And then it might be right to characterize what they're doing in output using the schema. So they're not using variables, but the schema a particular reasoning schema might properly characterize the disposition they've got to move from some inputs to some outputs. And if that doesn't depend on rich chain of thought prompting, then all is good. That's fine. So then we've got something that can do reasoning with its outputs, but then we're not yet a system that can move back and forth between taking advantage of all the content-specific knowledge it's got and then doing some reasoning on new things. I mean, if you're right, we're not miles away from doing that. It would just be a relatively small add-on. Why I think that it's not producing that by having a logic engine internally, I mean, my kind of reflective view is we really don't know enough to know, but I think the early hints are it probably isn't. It's probably going in for a different style of computation that allows it to get on the pattern in a different way.
Thank you so much. It was a great talk. There's work by Robert Yang, who's now at MIT, and other folks at Meta and Google, showing that if you train a network on multiple tasks and then you analyze the underlying representations, there is some kind of a compositionality emerging even in a random network in the representations. And another thing is if you ablate or lesion selectively some parts, you selectively impair those particular capacity across the different tasks that are using that particular capacity. So going back to your last slide, I wonder whether, so this is on the compositionality point that you have on the non-content specific that is emerging out of a content specific multitask sort of random network. Another thing is stable diffusion models, they try to get out of their weights the original image that they were trained on in an episodic memory type fashion, and they could actually get the original image out of the weights if they kind of ask the right questions. So it seems like maybe we are in a state where these kind of things are blurry, that these kind of connectionist approach seems to give emergence, maybe not unlike what happened at some point in evolution, not exactly like, but maybe similar in some ways, gives rise to these kinds of compositionality and kind of non-content specific. I wonder what you think of this blurriness.
So that's very helpful. So that allows me to talk about something that I didn't have time to talk about. So I was talking about general purpose compositionality. So I think compositionality comes in lots of different varieties. So compositionality is just the idea that you can put elements of representation together to get a new representation that's meaningful. I mean, a strong form, the meaning of the new one is a function of the meanings of the components, but we didn't even commit to that. And we can find that in various kinds of forms. You can find that in maps, you can find that in vectors, in state spaces. So I think you're right that as a kind of evolutionary hypothesis, we probably get degrees of it of different kinds. But I'm talking about something that's more like the kind of compositionality we have in natural language, which where you have the capacity to a first approximation to put together any representation that's subsentential with any other and get something meaningful. And I think I don't know the particular things you're talking about, I need to look at them. But the examples I know of where you find these different components that are making meaningful contributions within the activity within a deep neural network, you can put them together and you can recombine them in different ways, but in constrained ways. It's a bit like the way that you could move a point around on a map and it could represent different places, but it can't represent anything at all. So I think what you see there is like a limited form of compositionality that contrasts with the general purpose compositionality that we get with concepts or language. And the pairing I was talking about was particularly with that general purpose form of compositionality.
Hi, thank you, Nick. So, as you know, in the literature on inferences, one distinguishes between material inferences and logical inferences. My question generally is, where logical inferences would be, relations between propositions that actually follow logical rules, whereas material inferences could be, something like if it's raining and the streets will be wet, could qualify. For us humans, it can be, when we first learn logic, it can be quite hard to distinguish between these two. And my question is, how would you teach an AI to, that just operates on patterns to distinguish between these two very different kinds of transitions between inferences?
Yeah. So, I don't know how you would teach it, but there are things in prompt engineering that suggest that you can encourage it to do something that's more like material inference or encourage it to do something that's more like just inferring in virtual form. And it's not entirely clear. I was advocating humans using a reasoning engine, but it's not entirely clear that that's like a deductive reasoning engine. So it's not entirely clear that the difference that we're quite right to make in the logic class is something that we would find psychologically. So I'm not sure that I mean, as an engineering solution, that there would be a particular motivation for teaching the systems to make that distinction. Also, can Susanna come back? Sure.
I mean, I really just said really. So I mean, it seems like it would be hugely important to just maybe can you just elaborate on the very last thing you said? Everything else I was completely on board with.
So you're thinking it's important because it's a kind of deep logical distinction. Yeah. I'm thinking from the point of view of setting up something that's transitioning between representations. The thing that it cares about, the thing that will be important is if you put correct information in, are you going to get correct information out? And respecting this logic class distinction might not be very important for being set up to be able to do that. Oh, let's talk more.
So as grist for your mill, you might have seen like Russell's lab has this way for amateur Go players to beat the best Go engines by just exploiting the fact that the Go engine doesn't have a fully recursive definition of a group of stones. So if you just like, as I understand it, like if you just take it deep enough recursive layers of what a group of stones is, then it just freaks out and it'll lose to an amateur. And so he's been pushing, I think, a hybrid case as well. And I think you both make a good case, but I guess I just have a hard time imagining. I mean, it sounds like the architectures of hybrids that you're talking about are kind of like pipe the output of one into the input of another.
Yeah, I mean, that's one way of, I just wanted to highlight some ways of doing it. And that's one way of doing it, yeah.
But I guess I have trouble conceiving of one that's not like that, where in the processing in between, the implicit and explicit representations are somehow jumped back and forth. Is there any clue about how to do that?
So I think this second example is like that. So you have the same system and it's just chaining a bunch of representations, but you inject a prompt that says, right, in this current context, what you're going to be doing is logic-like. And then that might take you to entirely new bits of space. You might be doing that on representations whose meaning you've got very little grasp of. And then you inject a new prompt that says, right, now, given what you've been trained on, what sense can you make of this? So it's the same engine going back and forth between them. Let me just say another thing about Go. So as I understand the engine that AlphaGo uses, it is doing some of this too, because it's doing tree search across possibility space. So it's in some sense, it's already a hybrid, because part of the way that it solves the problem involves this kind of non-content specific reasoning on the logical structure of the problem space.
Okay, thanks. If we can assume that the world is more or less logical, or at least the non-mystic aspects of the world is logical and explainable. So in theory, if we train the large language models to formulate causal relationships hypothesis, then we could use logic to test these hypotheses and derive causal relationships. How do you think that might work?
Yeah, I'm not sure I completely understood, but I mean, you would think that if you train a system on something where there's a logical relationship, like it's seeing, like you do with babies and infants, it's seeing objects moving behind the occluders, you're adding and subtracting them. There's only one object. If it's not, you see it's not here, it must be there. You think that if there's a logic, the world is logical, if there's a logic behind the scenes that you've been trained on, then the system would discover that. And this same group, the Traylor and colleagues, have got a more recent paper this year showing that that's false, that it would be very, very useful for this thing to have discovered the logic that lies behind physical movement of objects, and it doesn't discover it. So I'm not sure we can go from thinking that the world's got a logical structure to thinking that the models we train are going to discover that structure. But I may have missed the core of the question. Yeah, I don't know. I mean, it's not the kind of thing that they've been set up to do, but when you put them in a package with some other bits of interface, they can do all kinds of clever things. So it might be that hypothesis testing is something that they could become a component of.
Thank you, sir. My question is, I'm working on works by Richard Nisbet, who talked about cultural differences in representation and cognition. So how do you put that in here? Like, for example, a word like individualism doesn't exist in Chinese. What he said was the most close word was selfishness. But if you talk to somebody from the Western culture, individualism is about, pride and doing things by your own. So how do you incorporate that cultural differences, cognition, and representation here? Thank you.
So I didn't mention this, and it's really important. So I think it's great that you brought it up. So I'm thinking of our trained content-specific dispositions, depending on the kind of input that we have to deal with. As humans, an awful lot of our input is about social situations. An awful lot of the way that we have of thinking about them comes from what we're getting from other people in our culture. There's one hypothesis that that's very driven by language, but we don't need that. It might be driven by language. It might be driven by other things that are culturally transmitted. But I think that will mean that the trained content-specific dispositions we've got for dealing with one another are going to be very much influenced by what's going on in our culture and probably our cultural inheritance. And that's why you'll get those kind of differences. And that is also reflected in the kind of biases you see in large language models that are trained on big corporate data. They end up reflecting the biases, both good and often pernicious, that's in that data. And that's why there's so much work on trying to put guardrails on them so they don't display that when we use them as tools.
Business or trade, those differences will come up.
Right. Yeah, no, I think that's right.
Yeah, so this distinction, content-specific versus non-content specific, seems really useful and important. And I guess I'm inclined to think both kinds of computation seem like.
I think Holly's got control of you,
maybe
so he can turn you up.
I said both kinds of computation seem really important, and it seems really useful to have them in our models. In terms of the application to deep learning, I'm just wondering to what extent this really requires an explicit hybrid model. I guess I'm inclined to think that if this, insofar as non-content specific computations are useful, then a really good machine learning architecture is going to learn to make those inferences without us building them in. I think you'd already see some evidence of that in some domains with existing models. For example, these GPT systems are super sensitive to contradictions. If they get P and not P, then they know instantly they're in trouble. And that just looks like an instance of a certain kind of non-content specific computation that's been learned. So do you have any reason to think that these things in the long run won't be able to just do all this by general machine learning?
No, when I was laying out the 3 empirical possibilities, that's one that's very, very live, that they can do everything, including being able to mimic this where it's useful by being trained end to end. I mean, there are some hints that they don't get onto it as easily as we might think, but it might be that in the kind of context where there aren't big resource constraints on training or on data, that it doesn't turn out to be a real constraint. So I mean, my central hypothesis is that when we're dealing with modeling humans where we've got very different resource constraints, we should expect that it's been hit on as a separate capacity that you can move back and forth between. So from that point of view, what might be most interesting in the modeling is the way that these systems can learn or otherwise get access to the capacity for non-content specific computation when they're modeling them in a much more resource constrained way. So, smaller models or smaller data sets or other kinds of constraints. That might tell us more about what the right way of modeling the human mind is.
I wanted to kind of probe your thoughts on the relationship between, you showed kind of like words like perceptual and motor and stuff in part of, in one of the slides on the difference between content specific and non. And I guess the example you gave of the chair, it's perceptual, but it seemed like you could describe that as non-content specific. Like you have general rules about rotation and objects can't intersect, and you could slot in different objects. You know, it's just Tetris, which could be thought of as a logical problem. So what is the relationship between something being more perceptual and interacting with the physical world and it being content specific versus non-content?
Yeah, no, that's a great question. So it's not automatic or built in that the way of interacting with the visual world should be content specific. Someone was talking, I think on Friday, about the summer project of doing vision using the tools of logic. And of course, we can get some way to doing like visual transformation, say, by explicitly encoding the mathematical principles of how objects change, and then doing logical type inferences on those. And it could have turned out that that was, you know, the way of doing visual motor processing as a practical application. But I think what we've discovered, that at least at the current state of the technology, if we want practical applications that can do visual processing or can do visual motor processing, it's more, we're more likely to hit on those using end-to-end training and then kind of building in content-specific dispositions. So I'm taking that as like one line of evidence that when I'm doing visual rotation with my trained visual motor system, that's not because it's got explicit representations of the laws of physics, but that it's been trained up with a huge amount of data about what happens to objects under the various things I can do about them, and it's been set up with a bunch of dispositions to move between representations that implicitly encode that information, and that's what I'm relying on. But that's a substantive empirical question, whether that's true or not about the visual system.
Thanks. Thanks, Nick. This was really interesting. I wanted to ask you to speculate a little bit about human cognition. So I was wondering, if it turns out human cognition is like a hybrid system, is the picture that like the stuff that happens in working memory is the content non-specific, more or less? And also, do you have a speculation as to why it would be so bad at like logic and probability theory? Is the view that it's like, oh, those are not the non-content specific inferences that we're good at, and there's this other system that is? And if that's the picture, then do you have a sense of what that system that we are really good at?
Right.
Yeah.
So I kind of agree with you, but in another way, we're not so bad at logic and probability, because if you give us logical probability problems in domains that we know how to deal with, we're extremely sensitive. And our visual systems can deal with probabilistic information in a way that, you know, does this very, very rapid updating that looks probabilistic and, you know, close to Bayes optimal. So it's not that our computations can't deal with probability, it's that there's a certain kind of explicit probability problems that we tend to get wrong. And I think that's because then we're dealing with them with this learned capacity to do non-content specific computations. So I think what humans are doing for that kind of computation is probably a culturally acquired special skill. So it's not just that we're using working memory, we're using working memory in a way that we've learned how to use it. And that means that it's, you know, prone to all kinds of errors. And then the first part of the question is to speculate. So I'm already speculating even more than I was in the talk. But yeah, I guess the speculative picture is that at least when we're doing these novel things, so when we're thinking about generally novel possibilities by putting together thoughts in a novel way, you know, a person riding on a javelin towards the speed of light, that we're doing that with something like labels in working memory. So we're forming some sentence-like structure over concepts in working memory. And then that's the kind of thing that can drive these sensory imaginings, and we can get information out of the sensory imaginings, but that's also the kind of thing over which we can perform logical inference. So that's one way of playing out the picture. But yeah, so it's nice to have a version of the picture, but I'm not really sure empirically that that's the best way of playing it out.
So I thought I understood everything until the answer to the last question. I thought the standard take on the Wason responses that you were good at was like content specific reasoning, because you were so familiar with what contingencies in the domain, you were good at that. But then I thought in the answer you were just saying that's a case where you're doing non-content specific reasoning, but you can only do it in a limited domain. You can't do it on the more abstract stimuli? I'm just clarifying what the
So
answer was to make sure I'm tracking.
I was thinking that Veronica was asking, when I'm doing the Socrates inference, how am I doing that? And then if I, having done a bit of the Socrates inference, I then imagine something, how am I doing that? But you're asking, what if I'm asked to do the inference about cards and numbers and so on? And people can get that right. And there are various kind of prompts that will lead people to get that more right. But now you're asking, why is it much easier in the Wason setting? And I think that is for the reason that we're pointing out, and that Ida showed us that deep neural networks do too, which is that if it's a sphere we're familiar with, we can rely on our content-specific dispositions for dealing with that kind of subject matter. So is there a problem with thinking that the representations that you hold in working memory can be processed by these content-specific trained dispositions, and they can also be processed by our capacity for non-content-specific reasoning? That's what I'm assuming. Okay.
So I have a question about kind of the same thing, I guess, to follow up on it. I'm not totally clear on the difference between content specific and non-content specific, because when I think about like how do you know that a human is doing non-content specific reasoning? Maybe you look at something like their ability to kind of follow through a syllogism, right? But the act of like sitting down and considering a syllogism is like a very specific context that like only very few people are used to engaging in. And this is one reason why like people might perform very, very differently on these more abstract tasks that are unfamiliar with them, right? And like the manipulation of symbols according to some pre-decided set of rules, like this is actually a very contextual skill, as the Wason problem like shows us, right? And so like, then when we look at language models, you say, well, it's doing stuff that's kind of content specific, but actually what it's doing is manipulating tokens and words and symbols, which is a kind of skill that it seems to me is associated with non-content specific reasoning, right? Like it gets me thinking about like Moravec's paradox kind of things, where like you might expect that a system is actually going to be more natural at manipulating abstract symbols than like deeply understanding intuitive kind of situations, visualizing space and that sort of thing. Like this would be the distinction that I expect. And like, how can we make the distinction between like non-content specific reasoning that is inside the representation versus context specific reasoning about symbols?
Yeah, okay. So I think this is difficult as an empirical question, but part of what I want to do as a philosopher is like pin down what it turns on. Okay, so as you say, there's lots of ways in which even the very reasoning thing depends on context. So this isn't just context sensitivity versus not. It's a very specific thing. So take a neural network after it's trained, take any other system when it's doing what it's supposed to be doing, and look at some transition it makes from some representations to others. So I go from thinking that all men are mortal, thinking that Socrates is a man, and I move from that to Socrates is mortal. So that's one question is how to characterize that disposition. Now, if it's right, given the counterfactuals and so on, to characterize that disposition as the disposition to move from anything of the form of the first two to the form of the latter, I'd say that's an instance of a non-content specific transition. Why? Because once you've like properly characterized what the disposition to move between transitions, between representations is, you ask whether the goodness of that, so it's being faithful to content. For these purposes, we can think of the correctness preservingness of that, whether that, which representations does that turn on? And for the logical ones, it's correctness preserving because of the meaning of things like and if then, but its correctness preservingness doesn't depend on human and mortal and Socrates. So that's what it's that very specific thing that the distinction's got to turn on, and I want to build out from that these other properties. So then it's, I think it's completely fine to think that to do this non-content specific thing, it can only be done in certain contexts or with only certain kinds of training and so on, because that's not what it's turning on. It's turning on what backs the faithfulness to content of the disposition to transition.
Okay, let's thank Nick. The next talk is 11:30, so we've got a coffee break until then.